Shall we start? Okay, so it's great pleasure to have Tamar Faran from Princeton University. He got a PhD at Hebrew University in 2022. Then, not sure. Now, postdocs at Princeton University. Today, she will want to talk about relativistic pistons. Please.
So this is the work we've been doing this past year with Andrei Gruzinov at NYU and IM. And what we basically find is a new type of self-similarity that is that we find when relativistic clustering. To our knowledge, this is the only example of this new type of self-similarity. And this is basically what I'm going to talk about. But first, the benefit of those who are not very familiar with self-similar solutions, I will give a very brief introduction to self-similar solutions, so the various types of self-similarity, and then I will get to our work. So if we're considering a problem where there are no typical or special dimensional scales, such as a special length scale or a special time scale, then we basically can take our set of PDEs that we want to solve. In our case, it's the fluid equations that have two independent parameters, the radius and the time. And using the appropriate variable transformation, we can transform the set of PDEs into a set of ODEs that instead of depending separately on the radius and the time, they depend on a single self-similar parameter that I call it Xi, it can be called anything. And these ODEs, which are the self-similar equations, are much easier to solve. And they can even be solved analytically in some cases. So it gives us a great mathematical simplicity to the problem. And it also gives us some intuition about how the system behaves at late times where there are no special dimensional scales. And what this means is that if we can find a correct variable transformation that would give us a self-similar solution, it basically means that the solution looks the same under stretching. So if we follow, for example, if we're solving for the pressure in the fluid equations, then it means that if we're looking at the profile of the pressure at various times, if we stretch the axis at the appropriate amount, which is time dependent, the solution remains the same at all times. And maybe the most popular example that everyone knows is the self-similar solution for the heat diffusion equation. So this is just a simple diffusion equation for the temperature. So theta is the temperature and kappa is the diffusion coefficient. And here on this plot, I'm showing the profile of the temperature as a function of the spatial coordinate x at different times. So the initial conditions is a very large concentration of energy density at some point, x naught. And then the various profiles are the profile of the temperature at different times. And you can see that these profiles become shallower and also wider. And it's very simple to show from the equation that the typical width of the profile depends on time in this manner. So it goes like the square root of the time. And the peak of this profile changes in the opposite proportion. So like t to the minus 1/2, just from energy conservation. So it's a very simple problem. So if I normalize the axis, so instead of looking at just x, I look at x over the square root of kappa t. And instead of just the temperature, I look at the temperature over kappa t to the minus 1/2. And I plot all of these profiles on top of each other. You can see that they all form one single curve. So this means that the problem doesn't depend separately on the time and x and the special coordinate, but it depends on some special combination of the position and the time. And this actually shows us, it's a demonstration that this system behaves in a self-similar manner. But I'm not going to talk about the diffusion problem. I will actually talk about ultra-relativistic blast wave, ultra-relativistic explosions. And but first, I will start with the Newtonian analog of the ultra-relativistic blast wave, just because it will give us a very, very important intuition to what happens in the ultra-relativistic case, which is much more complicated. So the strong explosion problem is just a point explosion that we create at the center at some point. We put in a large amount of energy that creates an explosion and a shock wave, which is this black contour line. And this shock wave propagates in a density profile that goes like a parallel r to the minus k. And when we solve the fluid equations, what we want to find is how the pressure, the density, and the velocity behave in time and as function of position inside this blast wave. And you can imagine that if we look at this problem at long times, so the initial length scales that existed in the problem, which are the perhaps the length scale over which I created the explosion and the mass that I exploded, will no longer be important after long times when the radius of the shock wave is much larger than the initial scale over which I exploded. I put in this amount of energy. So we expect this problem, this blast wave, to behave in a self-similar manner. And the self-similarity will be characterized by the behavior of the shock wave with time. So since we are considering a parallel density profile, we can also imagine that the radius of the shock wave will evolve like a parallel with the radius or the time. And the characteristic of this evolution is this parameter alpha that depends on k, which is simply the parallel exponent. So since I expect this system to behave in a self-similar manner, I'm informed by the behavior, by the expected behavior of the problem, and I choose this similarity variable that I call xi, which is just the radius normalized to the shock radius. And the unknown similarity exponent that I need to find in order to transform my PDEs into a set of ODEs is this alpha that characterizes how the shock evolves with time. So I need to find this alpha parameter in order to get the ODEs that I will then solve and perhaps obtain a solution, an analytical solution or a numerical solution, but anyway, it will be much simpler than solving the PDEs. So this type of this system of with the problem of a strong explosion can in general exhibit two types of self-similarities that were classified originally by Zeldovich. So I will just demonstrate the classification that was done by Zeldovich originally. So the most common and most simple type of self-similarity is called first type self-similarity. And Zeldovich classified this type as a problem where you can use dimensional analysis, dimensional considerations, in order to find this desired similarity exponent, alpha, the one that we're looking for. And to phrase it differently, it means that in the context of this strong explosion problem, it means that we can use energy conservation. We can require energy conservation in the self-similar domain in order to find this alpha parameter. So what I'm doing here is I'm simply integrating over the energy density in the problem, and I'm making the transformation to the self-similar function. So this is simply the time dependent part of the self-similar functions, and this is the integral that depends on the self-similar coordinate xi. But the important thing that I want to require is that the energy is constant in time. And when I require that this part is constant, then I get the very famous result that was obtained by Sedov-Taylor von Neumann, where alpha depends on k in this way. And once I have alpha, I can transform the PDEs into ODEs and solve the equations and obtain the self-similar solution. However, this is not enough, because in addition to requiring that the energy is constant in time, we also need to to require that the energy in the self-similar solution is finite. And it turns out that this integral diverges if k is larger than 3. So if k, this exponent of the density profile, is larger than 3. And so first type self-similar solutions only exist for this problem for k smaller than 3. So what do we do if we want to increase k and work with a steeper density profile? Then we enter the regime of second type self-similarity, and Zeldovich tells us that in second type self-similarity, it means that we need to solve an eigenvalue problem in order to find this desired alpha parameter, which is the similarity exponent. And practically what this means in our problem is that when we increase k, the shock wave starts accelerating and it loses causal contact with the flow behind it. So in the equations, what we see is that we have a singularity, okay? And in order for the solution to be smooth, we must eliminate the singularity from the equations, and this constitutes our eigenvalue problem in this case. And in order to eliminate the singularity, we must choose the correct alpha parameter. In this case, it's not analytical, it's numerical, and this is how we find the alpha that corresponds to the second type self-similar solutions of the strong blast wave problem. But it's not the end, because not for any k value, the solution is trying to pass through the singularity. For some k values, the solution doesn't even want to pass, is not approaching the singularity at all. So we need the singular point to actually be in the solution domain, in the domain of the solution. And it turns out that if k is smaller than 3.25, the singularity lies outside of the domain. So we don't even have an eigenvalue problem. So this is valid only for k larger than 3.25. So you can already see that we have a problem. We have a gap in our solution when k is between 3 and 3.25. So when it's k smaller than 3, we know it's first type. When it's larger than 3.25, it's second type. But what happens in between, we don't know, because Zeldovich only classified 2 types of self-similarities, and we don't know any other type of self-similarity. So that's a problem. And this problem was actually solved 20 years ago by Andre. Andre looked at the solution for the similarity exponent. Now I'm plotting alpha -1, which is the scaling of the shock velocity, shock radius. And what he said was this: okay, so at k equal to 3, I see that the shock moves at constant velocity. It's not accelerating, not decelerating. And on the other side of the solution gap, it also moves at a constant velocity. Alpha -1 is 0. So he said, okay, the simplest thing that I can do is just do that inside the gap region, the shock always moves at a constant velocity, because it doesn't make sense that it would do anything else. This is the most, the result that makes the most sense. And it turned out to be correct, and he also had a physical interpretation of this. It turns out that there is a piston, an infinitely heavy piston that contains most of the mass and the energy in the solution, and it lies partly inside, partly outside the self-similar flow. And since this piston is infinitely heavy and also causally connected to the shock, it means that piston cannot be slowed down and cannot be accelerated, because it's infinitely heavy and it's the source of energy in the problem. And what this implies is that the shock, if the piston moves at a constant velocity, the shock must also move at a constant velocity. And this explains this very trivial solution in the gap region. And Andre classified this new regime as a self-similarity of third type, and its distinction will become clearer when I talk about the ultra-relativistic case. So these are solutions that are driven by pistons. So these are quite trivial pistons, as you can see, because these pistons move at a constant velocity. But a more interesting and a much more complicated case arises when we're looking at ultra-relativistic blast waves. So essentially, we're looking at the same setup, basically the same problem. Only now the energy that I'm putting in the explosion is much larger than the mass that I'm exploding, and so I'm creating an ultra-relativistic blast wave. So I'm no longer the relevant parameter is no longer how the radius of the shock evolves with time, because it's obvious that the shock moves at roughly the speed of light. But now the relevant parameter would be the scaling of the Lorentz factor with the time. So now you're looking at this parameter m of k. K is again the exponent of the density profile, and we need to find this m in order to gain our self-similar ODEs and solve the equation and get our solution. And so this is a spherically symmetric problem. I'm actually, and now I'm looking at this new similarity exponent, and also my similarity variable is a bit different. It accounts for the distance behind the shock in units of this scale height of the problem. So R shock divided by the Lorentz factor squared. It's a bit different, a new similarity variable that is appropriate for our problem. I'm actually looking at more at a simplified problem. I'm looking at the problem, it's the same blast wave problem, only now it's not spherically symmetric, it's plane parallel. So the cross-section is constant. The only thing that's changing is this scale, where the radius of the shock is moving. But everything else is the same, the ambient intensity profile and the scaling of the shock. And so again, this is my similarity parameter. And now I'm defining the new self-similar functions, g of chi and f of chi. G corresponds to the profile of the Lorentz factor. And this is the time-dependent part of this of the Lorentz factor. And f corresponds to the profile of the pressure. And again, I can be guided by Zeldovich classification and look at first type solution and second type solution. So I'm starting with first type solution, and in the same way as in the non-relativistic explosion, now I'm saying to myself, okay, the energy is a relevant parameter in the system, and so I need to require energy conservation. So I'm writing here the integral over the energy density. I'm separating the parts that depend only on chi, which give me the profile, they're not time dependent, and the time dependent part. And you can already see that the answer is very simple. In order for the energy to be constant in time, m must be equal to 1 minus k. This would give me a constant energy. And then I plug in this value of m into the equations. In this case, Bluntfeld and McKee found that there actually exist analytical solutions to these equations. So G and F have analytical expressions like this R and chi. And then this integral can be written in this way, the power of chi. And in order for the energy to also be finite in the self-similar domain, I must have k which is smaller than 7/4. And so if I want...
You are talking about the plane parallel case? So I'm just confused.
Yeah, plane parallel.
Oh.
Plane parallel.
I see.
Yes. So if I were looking at the spherically symmetric, I would have r squared dr.
Oh.
But now it's only plane parallel. So okay, for first types of similarity must be smaller than 7/4. But now if I want to increase k, you can imagine that now I will go into the regime of second types of similarity. And in the same manner as in the non-relativistic case, now the shock loses causal contact with everything behind it. As I increase k, as the density profile becomes even steeper, I have this singularity in my equations, and this is again my eigenvalue problem, where I'm requiring that the solution passes smoothly through the singularity, so I eliminate the singularity, and immediately I get the value of m, the similarity exponent that I'm looking for. But again, in the same way, the solution is trying to pass through the singularity only when k is larger than 2. So you can see that also here in the ultra-relativistic case, we have a solution gap where the self-similarity is not of first type and not of second type. we assume, because now we have intuition from the Newtonian case, we assume that now this solution in between first type self-similarity and second type will be of third type. We assume that there will be some kind of a piston pushing and pushing the shock wave, creating the blast wave behind it. But now, as opposed to the Newtonian case, these pistons will not be trivial. And the reason is that we're dealing with an ultra-relativistic gas that is initially hot. And this hot gas is also accelerating. So, and it's accelerating because there is exchange between thermal energy and bulk kinetic energy. So these pistons will not move at constant velocity. We cannot say that now the shock wave moves at constant velocity because there is a piston. There will be some kind of a non-trivial dynamics due to this hot and relativistic accelerating piston. And this is the solution we were trying to solve. I'm sorry, this is a problem we were trying to solve. Okay, so to recap, our problem is that the self-similar scalings that we get from considerations I just described give us a diverging energy in the self-similar solution when we try to integrate the energy density in the entire domain. And the direction that we take is that we realize that we need to study the asymptotic parts of the flow far behind the shock, where the energy is diverging, in order to understand what is actually happening in the solution. And perhaps this will give us some clues on how to proceed, what we need to look at. Okay, so it turns out that for any value of m is the similarity exponent that we do not know, but we can say that for any value of m in the gap region, the solution of the flow far behind the shock actually asymptotes to power law solution in the Lorentz factor and also the pressure. So the Lorentz factor, you can see that it goes like t to t over x, so it's decreasing. With x, x is a new coordinate I'm using. It is equal to ct minus r. Okay, so ct minus r here it's 0, and it increases behind the shock. The shock is not included in this picture, but it could be somewhere here. So gamma squared decreases, and the pressure increases. Increases like a power law of x. Beta is a positive number, and you can see that if we assume that this self-similar solution is correct in the entire space, we would get diverging energy. And of course, this is impossible. But this is the asymptotic solution, no matter what the value of m is. A very interesting thing that we can see from this kind of behavior is that these profiles actually agree with the description of expansion into vacuum. Expansion into vacuum is defined by a pressure that goes to 0 at x equal to 0, as you can see happens here, and a Lorentz factor that goes to infinity at x equal to 0. So this is just the asymptotic solution behind the shock is just the solution we would expect from expansion into vacuum. But for real physical expansion into vacuum, we start with initial conditions that have a finite amount of energy. We expect the solution at some given time to have some kind of cutoff in the pressure. And this cutoff will make the solution consistent with finite energy that is not diverging. And so in general, if we start with some initial profile and we let the system evolve, we expect there to be a part that behaves like this self-similar asymptotic, and this will constitute the self-similar flow that is supposed to eventually connect to the shock. And in the back part of the profile, we expect to find some kind of a non-self-similar flow. And this non-self-similar flow, of course, it's not self-similar, so we did not get it self-consistently when we made the self-similar transformation. But if we solve for the entire system, and if we find a solution for expansion into vacuum without assuming self-similarity, we expect to find this cutoff here. So our strategy would be to find solutions that describe expansion into vacuum and then ask ourselves what kind of shocks can be driven by these profiles that expand into vacuum.
I have a question.
Yeah.
So the violation of self-similarity requires some scale introduced to the problem. And you think that the scale is given by initial condition?
Yes,
Okay.
there is, yeah. Actually, what we find eventually is that this part and this part separately, they evolve in a self-similar way, but you cannot find one solution that is self-similar.
Gamma is proportional to T over X.
Yes.
To the X, so
It's easy to derive from from the equations if you just from, I mean, if you're looking at some fluid element that is shocked at some point, and you assume this holding some assumption. If you assume that this fluid element, the Lorentz factor of this fluid element evolves like a power law with time, it's a fair assumption, but it's an assumption, then you immediately get this. And this Q, this is some constant, it will depend on the way this this fluid element decelerates. If it decelerates like a power law with, of t to some power, then this power would go into this coefficient. But the rest is easy to show. Always, I can show you. Yeah, and once you have this, then this is easy to get. Okay, so we're looking for solutions that describe expansion into vacuum, and then we're going to infer the shock properties. And this is our initial conditions. We assume some kind of initial conditions that are quite general. So first of all, the initial conditions are consistent with finite energy. You see we have some kind of an increasing pressure profile and then decreasing, so the energy is constant. The front part of the profile will be required to correspond to the correct power law asymptotic that we expect would evolve behind the shock wave. And then the rear part of the solution will be some kind of an arbitrary profile that is chosen just so that there would be some kind of finite energy in the solution, but we eventually find that the exact details of this rear profile will not affect our solution that evolves, whatever develops close to the shock is not affected by this rear solution at the back. Okay, and so you can imagine that finding an exact solution to these ultra-relativistic fluid equations with some kind of an initial distribution of the energy density without assuming self-similarity would be quite complicated, and it was, but we managed to do it thanks to a trick that Andre knew about that exists in Landau and Lifshitz fluid dynamics. And the trick is, in Landau and Lifshitz, they're looking at the Newtonian fluid equations, and they make some sophisticated variable transformation, and they transform the two equations for the in our case, it's a conservation of energy and momentum. After this sophisticated transformation of variables, we get a much simpler PDE. So instead of two PDEs, we get one PDE that is much simpler than what we started with, and it's actually a sort of form of a Klein-Gordon equation. Now, this psi that I will not get into is some non-intuitive combination of the Lorentz factor, the pressure, the time, and x. It's not intuitive, so I will not get into it. But the base of this equation is u and v, independent variable, are actually important. So these u and v parameters are actually the Riemann invariants of the problem. And what are these Riemann invariants? So we're looking at perturbation, the trajectory of perturbations in the t and x plane. This perturbation moves at v, the local fluid velocity plus the speed of sound. I'm putting in parentheses because this is a relativistic summation of the velocity. And so this C plus characteristic carries a constant value of u. U and V are just combinations of the Lorentz factor and the pressure. And this C minus characteristic, which moves at minus the speed of sound relative to the fluid, carries a constant value of V. So each intersection of C plus and minus characteristic actually give us the value of the Lorentz factor and the pressure at this point. So basically, instead of working with the Lorentz factor and the pressure, we're working with these Riemann invariants, U and V. And in order to solve the problem, we take this very simple equation, we apply our initial condition, and what we find for the pressure profile is this. So this is the pressure profile at some given time. This is the exact solution to the equation without assuming any self-similarity. First, we find this, which is very trivial, that the energy in this solution is finite. You see it's not diverging, of course, because we started with finite energy, so it's not surprising. And we also see that this pressure profile is composed of two basic components. First of all, we see that the front part of the profile agrees with the power law asymptotic that we expect would form behind the shock wave. So the shock is not included in the solution, but we expect it to be somewhere here at smaller x, and that behind the shock there would be this power law asymptotic would develop. So we're happy that the general profile agrees with the power law asymptotic, and we also see that behind this self-similar part of the flow, which is where the power law asymptotic is, there is this pressure peak, and this is where most of the energy is stored, and that's why we call it the piston. So this is what we actually expected from the beginning. We expected there to be some kind of a piston where most of the energy is, and there in front of it, there will be this power law asymptotic, which will eventually connect to the shock wave. And so now we can ask ourselves, now that we have the exact solution for expansion into vacuum, we can ask ourselves what kind of shocks can be driven by these pistons that are expanding into vacuum. And the requirement from the solution is that the shock will coexist with the piston and with the power law asymptotic. And what this means in practice is that if we are looking at the solution at some given time, and we have this power law asymptotic and the piston, now we need to fit in a shock. We want the shock not to ruin this profile behind it, so that if you look at the solution at a later time, this power law asymptotic this region of the power law asymptotic will grow, the shock will still exist, and we'll still have the piston. That's what we want to require. And if we can find this kind of solutions where the shock evolves self-consistently with everything behind it, this would probably be our solutions for the shock. And in order to find the condition on M, the similarity exponent, it's actually simpler to look at the solution in the UV plane. So these are the axes here are the Riemann invariants, U and V, which are functions of the pressure and the Lorentz factor. And actually the solutions are characterized by this parameter lambda. Lambda is simply a combination of M and K. It characterizes the power law asymptotic behind the shock. And for each lambda, we can plot this line here, where U is equal to V over lambda squared, that just characterizes the boundary between where the solution would agree with the power law asymptotic and where the solution in the part of the solution that would contain the piston. And if I want to plot the solution in terms of U and V at various times, these contours of equal time give me the relation between U and V at each given time on this in the space of U and V parameter. So this part of the solution would give me the power law regime, and this would give me the back part of the flow where we have the pistons. Same for this. And now, what do we expect the shock to do? I want to plot the shock in this space of U and V. So if the shock does something like this, then this is not good for us, because you can see that this is the shock trajectory. Here at this time T1, we still have this region where the solution behaves like a power law, and then the back part. But then as we move forward with time, we can see that the shock eats up parallel asymptotic space, and it basically ruins the solution. So the shock does not coexist with the piston and with the parallel asymptotic. So if the shock does something like that, it's not good. It's probably not describe a piston that drives a blast wave that drives the shock. But then if the shock does something like that, if it's either parallel to this line, or if it's shallower than this line, and you can see that the parallel region is maintained, sometimes maybe it can grow. So if the shock does anything between here and here, then it's good. So if we want to formulate this condition in terms of equations, then we can just using jump conditions at the shock, we can write this derivative, the expected derivative of the shock, which depends on m and k. So the slope will depend on the values of m and k, and we want it to be shallower than this line. This is the only thing. But it turns out that the only solutions we can find are solutions in which the shock is parallel to this line. So only this equality can exist, and this immediately gives us the desired similarity exponent m of third type self-similarity. So here, in this, we solve the problem. So now the gap is closed. We no longer have this gap, but we have this connecting solution between first type and second type self-similarity. And just to summarize why this is so different. So in first type self-similarity, the similarity exponent is determined by the requirement for energy conservation within the self-similar flow. And in second type self-similarity, we solve for the eigenvalue problem. So we eliminated the singularity that existed within the self-similar flow. But in our new solutions, third type self-similarity, what led us to the solution is the understanding of the physical behavior of the piston. And the piston lies fully outside of the self-similar flow. So in order to find, so the special characteristics of third type self-similarity is that in order to find the value of the similarity exponent, we need to understand what happens outside of the self-similar flow. So it is the non-self-similar flow that determines the similarity exponent.
So what is happening at the boundary between the type 1 and the type 3 and the type 3 and type 2?
What's happened?
Yeah.
So you can assume, you can expect nothing very special is happening. So there's no jump or anything special happening here. But but actually, when you look at k equal to 7/4 and you follow the asymptotic profile from the shock backward, then actually the pressure is constant. So k smaller than 7/4, pressure is decreasing behind the shock, and then as you increase k, it becomes flat, and then you have this decrease behind, at the rear part of the solution, and then when you enter this point, then the pressure behind the shock starts increasing. So it's in this line, actually, it's the transition between constant pressure and then increasing pressure. So
your method is also applied to the type 1?
In type 1 self-similarity, there is no piston, but it does apply to type 2.
Type 2.
And in type, I have actually go to this slide. So I wasn't going to talk about this, but actually this condition, when I solved for, when I solved this equality, one hidden assumption was that lambda is finite. But then if I take lambda to infinity, this is just a line that coincides with the x-axis, then I actually get m of second type self-similarity. And so this distance actually describe what's happening behind the parallel regime, this parallel asymptotic, and behind the self-similar flow in second type self-similar solution. The difference is that in order to find the similarity exponent in the second type solutions, we don't need this because we have this singularity and we expect the solution to be smooth. So this immediately gives us the value of m. But if you're interested in understanding the physical solution in the entire space, then it will be characterized by these pistons, and you can use these solutions. It's not relevant only for this tiny gap, but it's actually relevant for wider range. In first type self-similarity, there are no pistons because most of the energy is close to the shock.
Does this analysis depend on the choice for the energy? You chose an energy profile at the beginning, like initial conditions, actually. What if you change that profile?
So the front part of the profile, I have no freedom because I want the front part of the profile to agree with what I expect to evolve behind the shock.
Okay.
So there I have no freedom, but I do have a freedom in what I choose at the back. And it turns out that since there's hardly energy there, it does not affect what's happening. It does not affect the piston because the piston has most of the energy, so it cannot affect it. And it also doesn't really affect the power loss symptotic that evolves behind the shock, even though information does come from the back part of the profile, because there is hardly any energy there, it does not affect the solution. I only have one last point concerning the piston. So it turns out that while this part does depend on M and K, this part where it characterizes the piston is independent of M and K. And so basically all pistons that expand into vacuum have the same dynamics. So we find these universal exponents that characterize the pressure, the Lorentz factor, and the position of this piston. So the pressure goes like T to the -1. The position goes like T to the 1/4, and then the Lorentz factor at this point goes like T to the 3/4. And so these are universal parameters for these giant pistons that expand into vacuum, and they don't depend at all on what's happening at the front. So they don't depend on M and K, which means they don't depend on the medium, on the shape characteristics. I guess that's it. That's the summary. I'll just reinstate this. So I think the main point is that we kind of define the classification by Zeldovich. So type 1 and 2 are the types of self-similarity where the exponent is determined by the self-similar flow, by the behavior of the self-similar flow. But then third type self-similarity, the self-similar behavior is determined by the conditions outside of the self-similar flow. So that's the main point. And this is an example of this new type.
I'm interested in actual application with your solutions. I guess type 1 solution applies to GLB aftergrowth, and type 2 is relativistic shock breakout.
Yes.
And the type 3 is, do you have any idea what kind of system we can apply? I mean, your type 3 solution holds.
I don't think the
One-dimensional.
Yes, I don't think this narrow range of landscape profile has some kind of professional applicability, but if you can think of some application where you need to understand the back part of the flow, which contains most of the energy, then this would
Your picture.
So it doesn't have to be third type, it can also be second type sub-scenario. But if you can find a scenario where you care about what's happening with the back, then these things would apply. Yeah, so I haven't thought about applications yet, but
Yeah, but your picture gives some more, I mean, your picture holds for type two solutions, so
We're type two. So this is just a planar case,
Mhm.
but this can be generalized, probably be more complicated. I will try.
but you're doing the extension of
Not yet.
Ex-
Maybe I will look at it. It will be more complicated. But I think if we do it for a spherically symmetric case, perhaps this can be more applicable.
Mm.
Things in astrophysics.
In general, such an ultra-relativistic explosion decelerate into non-relativistic regime. And in your three type of solutions, is there any difference in the behavior into the transition to mild relativistic and non-relativistic
Yeah,
behavior?
so we solve the equations we solve are all in the context of ultra-relativistic.
Yes, of course.
So then, so at some point you can imagine that the profile will become not visible. But
Yeah, I know, but
don't account for.
for example, because the pressure gradient changes, even the signature for your signature of the pressure gradient changes according to the type of solution.
Yeah,
I expect some difference is found for the deceleration behavior. Can you expect something?
so are you talking about the last wave that starts relativistic and becomes non-relativistic at the
Oh,
top,
yes.
or are you talking about?
For example, transition to self-terrorism.
Yeah, so we don't look at it in this case. We do have a different work that a back part of a Blandford-McKee plus wave. You have a decreasing Lorentz profile, a Lorentz factor that eventually the flow becomes milder relativistic and non-relativistic. So in that work, we do look at this transition, but here I did not look at it, but I expect it to not really change the dynamics because it would, I mean, given that and I put in enough energy, this transition would happen at the rear part of the profile, but where the energy is very low. So I don't expect it to really affect the dynamics in front of the
Okay.
Yes, shockwave accelerates actually.
They accelerate it.
So there is no transition to non-relative.
No, but
No,
the
just
flow.
accelerating.
The shock
Ah,
is only
ah.
accelerating.
So the behavior is
Okay,
different.
sorry. Oh, okay, I misunderstood. I thought you were talking about the profile behind the shock. So here the shock are accelerating, but you're right that if we look at the Lorentz factor, the profile of the Lorentz factor behind the shock eventually become non-relative. But that would probably
And what do you expect after such unlimited acceleration?
nothing
What do you-
usual.
Density
The
profile.
Lorentz factor is allowed to just like the pressure is decreased.
Mhm.
So eventually,
Mhm.
very low pressure, but you can start as
What may be,
pressure as high as you like.
but it may be very interesting point to be considered. What I thank you.
The spherical case, so usual Blandford-McKee solution is a kind of type 1.
Yes.
And type 3 also already obtained in the spherical case.
No.
No.
So
Ah,
so in the spherical case, so these gaps do not exist generally for every type of blast wave. In the spherical case, the explosion problem that creates a blast wave does not have a gap, but the implosion problem where the shock wave is converging, it does have this gap problem. So there will be some kind of third types of similarity converging perfectly symmetric case. Yeah, but we have not. Because
one other question, a little more general one. Is it possible to check stability of these similar solutions?
it's possible, yeah. We have not done that, but it's possible. It was not for the key.
Mm. sorry, Brandao-Mackie solution should be stable, right?
No, from what I know, they're not attractor. So if you start with something, so they assume spherical symmetry.
Yeah.
If you don't start with something that's completely spherically symmetric, it will not
You mean
evolve into.
You're talking about deviation of spherical symmetry. You are talking about deviation of spherical symmetry, right?
Yeah. So.
Yeah, but
There's a. Oh,
Mm.
what were you?
yeah. You're right. Yeah, sorry. No, I am asking the deviation from spherical symmetry.
Oh, okay. Yeah, so.
Okay, yeah, thank you.
For Taylor, I think if you start with something that deviates from
Uh-huh.
spherical symmetry, the solution will evolve into spherically symmetric.
Okay.
No, in the Bluntford-Leakey case, it's not the case. It's not an attractor.
It is not an attractor.
And here,
How about type 2?
type 2. I assume it will be the same, but I haven't.
Uh-huh.
I need to think, but I assume.
Other questions or comments? If not, let's Tamar. Okay. In 7 o'clock,
Well,
we will leave.